All right, thank you.
Okay, here we go. So let's, this is this journey we're on here. This is our crash course from Calc 1 of this problem. What do we know? We know how fast the quantities change every moment. We want to know how much we have at every moment. And our principle 1 was constant rate of change. What does 60 miles per hour mean? What does it mean if you're going 60 miles per hour? Yes, sir. Every hour you travel 60 miles. Is it true? It's true, but this is not what we want to emphasize. We want to emphasize that you know a lot more than that, right? You know a lot more than that. Yes, sir. Okay.
For every X hours, you go X times 30 miles.
60.
Hours.
60.
60? 60, yes.
You said 30. Yeah, so go ahead. What's that? For any variation in time, what happens?
You move to 60 times that variation.
You go a distance of, your variation in distance is 60 times that change in time. All right? So yes, you go 60 miles every hour, but you know a lot more than that. And we, in order to do what we're doing, you need to know a lot more than that, that for any change or variation in time, the change in distance is 60 times that change in time.
Assuming that the change in time is measured in miles, right?
Yeah.
Okay.
Yeah, change in distance in miles is 60 times that change in time. Okay, so this whole journey we're on in the first week, this is the core principle. This is what it's all about right here. It's all based on this. Okay? Principle 2 was a net accumulation function. And what does that do? That gives an amount of change in a quantity for any value of x when the rate of change is known, right? So we were looking at the flag and we were saying, how much change in the height do we have since 0.6 seconds, right? And that was the idea of a net accumulation function. It's a dependent variable as amount of change for any value of x given the rate, knowing the rate of change. Okay, principle 3 was that realistic rates are often changing rates, right? So we started with considering that the rate of change was constant, but often in life the rate of change is not constant, and we said this is where the problem becomes a lot more challenging, right? This is where the problem becomes a lot more challenging, but we want to take advantage of what we know about this, right? Constant rate of change in order to tackle it now when we have a changing rate of change. Okay, so I think on your sheet you have principle 4, right? Yep, is that where we're starting there? So principle 4 was pretend rate function, right? So what did we do? Last time with the pretend rate function, we looked at every interval and we said, let's try to eyeball it so that we're kind of picking an average, right? We're like picking one value of the rate that reproduces whatever's really happening with the rate in that interval. So it's kind of like an eyeball average method. Remember that? Okay? So this is not the one I wanted to see here. Thought it was. I just didn't get rid of all that. Yeah, this is what I want. Okay. All right, and so then we came up with those red segments up there, right? The red step function was like trying to be like the blue function, right? Trying to reproduce the blue function, but using constant rates. And we said the reason we wanted to do that was, why did we want to do that? Why did we want to change this beautiful, perfect, exact rate of change function into this very choppy, bad approximation? What was the point of that? Somebody knew, yeah.
So we could use the dy equals mdx to try to find out the approximate change in rate.
Right. So because now with these red constant rates, this new graph, we can use dy equals mdx to approximate changes in heights. So we're making progress towards this knowing what the height is at any moment. Okay, and so this is the table we came up with. And so just as a starting exercise here, looking at this table, where in the table do we have how fast the flag height is changing at every moment? Okay, talk about columns, not a column, columns. What columns represent this statement, how fast the flag height is changing at every moment. And then, where in the table do we have how much change in flag height there is at every moment? Again, don't talk about a column, talk about columns. Okay, so just take a minute or two to see if you can answer those questions for the person next to you. All right, so where in the table do we have how fast the flag height is changing at every moment? Where do we have that? Yes, sir, in the back. He wants the first two columns. What do you think? He said the first two columns. Agree with that? No, some say no. So how fast the flag height is changing, which column is that? Second, right? That's our approximate rate of change. And at every moment. Oh, I'm glad I asked. At every moment. We want how fast is the height changing at every moment? Which column is that? I've heard first, third, and fourth. It's the first. Time elapsed, right? So this is a function of the rate function. It's rate as a function of time. It's telling us what the rate of change is. So you were right at the beginning. It's the rate of change for every given time. So for all times between 0.6 and 0.95, our rate is negative 0.75, or approximate rate. For every time between 0.95 and 1.3, the approximate rate is negative 0.4. So this right here, this is our approximate rate of change function. Independent variable time, dependent variable rate of change. Okay, where in the table do we have how much the change in flag height is there at every moment? Yes, sir. He wants first and third. What's that? First and fourth. Okay, so all right, definitely first, every moment. So how much change in flag height? Oh, so I should have been a little more specific. How much accumulated? Okay, well then you were right. You were right. If you chose 3, I guess. Accumulated would be what? First and fourth. Yeah, so, but okay, so now this is not at every, this wouldn't really work because these are variations in change, right? These aren't how much change you have at a moment. These over here are how much change you've had so far at this moment. So like at the moment, 0.95 seconds, this is how much change you've seen so far, or the net accumulated change. So column 3 still didn't really work even without the change, okay? So because it's like how much change you have accumulated so far at the current moment. So our rate function is columns 1 and 2, and our net accumulation function, columns 1 and 4. Okay, any questions on that? So that's all kind of review. All right, so now what I want to do is I want to that second function we talked about, the net accumulation function, I want to get a sketch of that. I want to graph that. So that was what, columns 1 and 4. So what should I do to graph this? What should I do to graph this net accumulation function? What's that? We have a table, so we just have points, right? We just have points. So plot points, 0.6 and 0. And then we know at 0.35 seconds later, at 0.95 seconds, our accumulated change is negative 0.2625, wherever that is. So let's see, we're at negative 0.95, right here shy of 1, and just like right about there. Is that right? So when I plot these points, is it going to follow this, the exact net accumulation function? Is it going to follow that?
Roughly.
Do it. Go. So did it follow close?
Yeah.
It did?
Yeah.
And is that so we used intervals of 0.35. Is that necessarily the case, or is that what we would expect? Let's see. So what do we got? Negative 0.4. negative 0.4 is here. And then negative 0.7 approximately. Negative 0.84. Negative 1.05. Negative 1.26. And where's that? 2.7. Negative 1.435 at 3.05. And negative 1.7. How'd I do?
Pretty close.
Okay, so what about in between? So based on this approximate rate function, in between, does it have these curves like the one that we're after? If it's based on these constant rates of change, then what should it look like in between these points? Yeah.
Linear.
Should it be linear? Yeah, if we've got constant rates of change, we know that from 0.6 to 0.95, we have a constant rate of change, and we start here, we end up here. With a constant rate of change, we should have straight line segments. And that's the best I can draw straight here with my wobbly hands, like something like that. Okay, so just imagine those are all straight segments, okay? Adjoined at the points. Okay, so good approximation or not? Yeah, unfortunately it's good. Because we have huge, so we're using these, look at our rate function. How good is the rate function? The red pretend rate function versus the actual. Is it good?
Not very.
Not very good at all, right? So if I were to take away that blue graph and just show you the red one, would you guess that we were trying to mimic the blue one? You would never come up with that, right? You would never come up with that. So kind of coincidentally, the approximate net accumulation function kind of follows that the exact one, and that's more coincidence than anything. And we'll see a little bit later why that is truly coincidence. Okay, so where are we at here? All right, so how do we write this function? So we're going to call this capital A of x. This is our approximate net accumulation function. So where is that coming from? How are we getting these values? Suppose like this value right here at 2. At 2, we've got negative 0.84. Where did that come from again? Where did that negative 0.84 come from? Do you remember? Change in height throughout the period. Okay, but more specifically, how do we come up with that value? Yeah, so didn't we add up all these for each interval? We added up the individual changes in height. When you added this plus this plus this plus this, you got that, right? So generally speaking, and then how do we abbreviate a sum like that? Remember, we have summation notation, right? So this as accumulation function it's generally a sum of stuff, right? So every one of these values over here is summing up all the individual changes for each interval, right? So how did we get each individual change? So what are we summing up? Each one of these was what? How was it computed, right? So how did we get each one of these values? MDX, right? MDX. Each one of these was the rate times the change in x. So it's like we had the rate for the ith interval times our delta x value, right? And then I equals, starts at 1. And so this is like the interval number, right? So like I equals 1 to the number of completed intervals. So like for first we had the first interval, and we got that mdx, right? Then we had the second interval, and we had that mdx, and then the third, and then the fourth, and we added those four together, and that's what this notation means. It just means sum up a bunch of these, one for each interval, from in this case from 1 to 4, right? From 1 to 4. Okay, but then what about, let's use orange, how about, okay? So then what about if I'm in between, right? So that makes sense if I'm exactly at one of the endpoints of the intervals, right? Then I'm just adding up an mdx. But what about the, say this point in between? So that point is all this, the summation that we just talked about, plus a little bit more, right? So this part is that sum that we just did, right? So this amount of change in height to there, that's this first sum. But then we have this little bit more. And how can we calculate that little bit more? Well, it's still, we're still, the height is still changing at a particular rate. It's just the next rate, right? So it's the next rate. So we had the first 4 rates times each one times delta x. But now this little amount of change is at the new rate, right? So we'll call that the current rate. So if we're talking about something past 2, then we're at this rate, right? If we're somewhere between 2 and 3.5, that last little bit is going to be accumulating at this rate. Is it going to be delta x? Do we make it all the way through that interval? No, so it's going to be something less than. And so what it is, it's dx, okay? So dx is our variation in the current interval. So varying, that's the varying variation in current interval. So at any, so say at, right at this, let's say 2 point, where am I at? 2.25, right? At 2.25, to get the total accumulation, I'm going to add up from the 4 previous completed intervals. I'm going to add up all the mdx's. That's this plus this plus this plus this. Now I have a little more variation through like part of the interval at this rate. So I'm calling that rate the current rate. And then however far I've gone into that interval, I'm going to call it dx. And that dx will vary in each interval from 0 to delta x, and then start over and vary from 0 to delta x as I go through each interval. So this is a structure for the net accumulation function when we're using these pretend rate functions made of steps. Summing up all the variation from previous intervals that were completed, and then we have a little bit more like from a partial interval, right? We have a little bit more for a partial interval, and that's how much variation we have in that partial interval, and then that's the rate of the current interval. And that all together gives us that rate, that y value, which is the net, approximate net accumulation at that x value. Question?
Is the dx the same as the delta x?
No, right? So delta x is this fixed value of the width of our intervals, or variations of our intervals that we started with. Dx, then say as x changes from 2 to 2.35, dx will go from 0 to 0.35. So dx is varying. It's varying, and it's going to vary through the current interval. It's going to start at 0, and it's going to end at 0.35. Then it's going to start over for the next interval. Is it helpful? Other questions? Does it make sense? Okay. So this is our general structure for the net accumulation function when we're basing on one of these pretend step rate functions. And it comes right from the table, plus thinking about how we would get a little more accumulation if we were in between values, right? If we were in between. So then this covers them all. This covers all those values of net accumulation all the way down, not just the points we plotted. Okay. Questions? Yes, please. Yes. Yes. Right now we've fixed delta x at 0.35, and then dx is going as x changes through the intervals. Dx is going 0 to 0.35, then 0 to 0.35, then 0 to 0.35, then 0 to 0.35. So we can keep track of whatever little amount of accumulation we have in the current interval. And then that gives us the function for all x values, rather than just the points at the endpoints of the intervals. Okay, good question. Other questions? Okay, so you got that in there? All right. So we're still on principle 4, pretend rate function. So what did we do before? Before, to build that pretend rate function, we eyeballed, right? We eyeballed and did averages. Now we want to try a different, we're going to use a different method here, and we're going to call this the left-hand method. And what the left-hand method does is, rather than going to an interval and trying to eyeball it and find the average and stick it on there where we all get a different answer, so now what we want to do is, we're just going to look at that interval and we're going to get the exact rate from the left side of the interval, right? So the interval is like this. So on the left side of the interval, there is an exact rate of change. We're going to make that exact rate of change the constant rate for that interval. And then we're going to go to the next interval. We're going to look at the exact rate on the left side. And we're going to make that rate at the left side the constant rate for the whole interval. Okay? So you have... see if you can do this. Hopefully you've done something like this in Calc 1. So you're going to estimate, the first thing is you're going to estimate the values, and I have at the bottom of your sheet there, it says estimated values. So this is question 1. Estimate the values of the exact rate function, r sub h, that's the blue function, r sub h, at the left side of each interval. So you're going to fill those blanks in with numbers, using the graph, estimating what those values are. The values of the exact rate, according to the blue function, on the left side of every interval. All right? And then, those exact rates you estimated in number 1, those are unknown because we don't, you're just estimating them from the graph. We don't really know what this function is. I haven't told you. But those exact values can be expressed. Okay? So I want you to represent those exact values with math expressions. That's the second line at the bottom of the page. Okay? So what do we have? What notation or what tool do we have that we can actually represent those values exactly, even though we don't know their exact values? Okay? And then once you've done those first two things, then you're going to sketch that approximate rate function based on the left-hand method, not the eyeball average method. Okay, so you're either making progress. Oh, was a question? Yeah.
So to choose the left-hand side of each interval, we need an interval set at 5, so like 0.35.
Same intervals as before. Yep. We're going to start at 0.6. So those the vertical lines on there. You're going to same as before. Start at 0.6. Intervals of 0.35. Same intervals we had before. Yep. Other questions? Okay, you're either making progress or you're getting help. All right, if you're not sure, then check with somebody. Check with TA, check with people around you. With my numbers? Does it make sense? Do you agree with that? I'm looking at each interval, and I'm picking off the exact rate by the graph, and then looking at the y-axis to get an estimate of that rate of change. Exact rate of change at the left side of every interval, at the start of every time variation, I should also say. So yeah, it's the left side of the intervals, but we're talking about the starting time of every time variation. Agree? Are we good? Any problems with that? Okay, cool. Now, for instance, this one right here, is it exactly negative 0.7? No. But I want to express whatever there is an exact value there, and I want to express that exactly. How can I express that exactly? Yes, sir? Right. So we're going to use function notation. Gives these y values. So it's going to be, is that all you guys were raising your hands? That's what you're going to say?
Yes.
R sub h. So this is just an estimate, but R sub h of what? 1.3 gives whatever that rate is exactly. Function notation gives a value of the dependent variable. In this case, those are rates, right? The dependent variable is rate of change. So I can do r sub h of 1.3. And then what about this negative 0.1 here? So that's an estimate of what exact value? Yes?
Is the accumulation function we're using right now, r sub h, is that the one we used the other day? Is it different from the one we just created?
No, we're talking about rate function. We're working on this. This is the exact rate of change. And so now we're going to make a new pretend rate function with this new method, this left-hand method, rather than the eyeball average method. So to do that, to do this alternate way of coming up with the pretend rate function, we're going to pick off the rates at the start of each interval, at the start of each time variation, and then use those as the constant rate. So for this interval right here, second to last, that negative 0.1 is not exactly negative 0.1, but it is exactly what? Yes, ma'am? Okay. Yes. So this is what, yes, exactly. What does this mean? This is the rate of change, exact rate of change of height at 1.3 seconds, right? This is the value of the, it's not multiplication, this is function notation. That's the value of the independent variable, or time. And then this whole thing gives us the rate of change at that time. So it's exact, we'll talk about that later. So one more time. So this negative 0.1 is an estimate, but it is, yes, sir? He wants r sub h of 2.7. Agree? Yes. Okay, so now we want to graph this. So now we've picked off all the rates on the left sides. And so now to create the new pretend function, we're going to take those rates and make that the constant rate for the whole interval. So what's the constant rate for the whole first interval? Negative 0.75. I'm going to pick off the negative 0.75 and make it, or what, r sub h of 0.6, right? Exactly r sub h of 0.6. I'm going to make that the constant rate for that interval. Okay, what about the next one? Same thing. It's going to look like this. Okay, next one. Just about negative 0.7. Exactly what? R sub h of 1.3. And then I'm going to take that r sub h of 1.3 and make it a constant rate for that whole interval from 1.3 to 1.65. So what I'm drawing, this is what you should have done in step 3. You should have drawn. Okay, where's the next one? Essentially negative 0.75. Exactly, r sub h of 1.65. Okay, next one. Something like that. Next one. Oh, no. I used the right. I went into right mode there, right? So I went left. So we're going to go back to negative 0.75, or r sub h of 2.35. Come on. There we go. This one is, is that the 0.1 again? Negative 0.1. Last one. R sub h of 3.05. So here's, for the same intervals, starting at 0.6, variation of 0.35 seconds, here's the left-hand approach way of doing the pretend rate function. And if we do it this way, then we all get the same thing, right? There's no changes based on the eyeball average. If we use the left-hand method, we all get the same thing. How about this? Is this a good approximation of the rate function? Is this better?
I would imagine it's worse.
Well, in any case, they're both bad, right? So they're both bad. But certainly, again, if I just showed you the red step function and didn't show you the blue, would you come up with the blue function? Never, right? Never, okay? So let's take a look at the approximate net accumulation function for this one, okay? But we're not going to create it point by point. We're going to use GC to do it. Any questions on this page? Okay, here we go. All right, so here is, we're at 0.35, our interval's at 0.35, and we use the left method, and here's what it's going to look like. Ready? So here's time going by. On the left, it's generating the approximate. I need to show more here. Let's move over. Okay, so here's what the approximate accumulation function would look like for this pretend rate function. Same kind of thing. It's the, it's the linear segments, the piecewise linear function. You are evil. Go away. Okay. All right. Okay, so let's take a look here. It should have showed up, but it doesn't. There it is. Okay, anyway. So, bad approximate rate function, bad approximate net accumulation function. But it's something, right? It's a start. So this is a start. You're using MDX to try to take a changing rate function and get the corresponding net accumulation function. So we've talked all class about these bad approximations. So I want to do better. How do I do better? How do I do better? How do I get a better rate function? And then as a result, a better net accumulation function. Yeah, so most of you are probably thinking, I'm going to make a smaller interval. With a smaller interval, those constant rates are going to kind of do better at mimicking the actual rate, and then we're going to get a better net accumulation function. That's principle 5, 6? But this was page for 4. This is 4, right? So that's principle 5. You can get better approximate rate and accumulation by making smaller intervals. Smaller intervals. Okay, so let's do that. Let's do that. So what I'm going to do is I'm going to hold on to this one. This is for 0.35. I'm going to hold on to this one. I'm going to start over with a smaller interval. So there, I'm going to hold on to the thin one there, and that's for 0.35. And I'm going to, let's change it to, I'll just click here somewhere, 0.212. So now my interval is 0.212, and I'm going to let this one emerge, be generated, and we'll see what happens. So now so this is for, where's the grid? Okay, so now I'm going to use, this was for 0.35, now we've got 0.212. Watch what happens. Here we go, ready? So, do we have exact? Do we have an exact net accumulation function? No way, right? So this is still a pretty bad approximate rate function. So we would conclude that this new approximate net accumulation function is still pretty bad as well. Okay, and I'm going to hold on to that one now. So what was that? That interval was what? 0.212. Let's hold on to that. And I'm going to go back and start over here. And let's pick something smaller. Smaller intervals, say 0.0809. Here we go, watch. Look at the rate function. Is the rate function starting to, the approximate rate function starting to look like the actual rate function?
Yeah.
It's doing much better. So we could expect then that this new net accumulation function is much better too. Is it exact?
No.
No, okay. How do we know it's not exact? By comparing it to the last one. What's going to happen when we get exact? When we compare it to the last one?
The intervals are going to be infinitely small.
No, how are we going to know it's exact? By looking at the current net accumulation function with the last one we did for a bigger interval. Yeah, so, okay, so let's go to, what are we at, 0.0809? All right, so, and let's go even smaller. Not that small yet. A little bit bigger. So from 0.08 to 0.02. Here we go, watch. How's the rate function now? Pretty dang good. How's the net accumulation function? How does it compare to the last one? Are they the same?
No.
Almost. Almost. So let's do one more time. What was this? 0.02? 257?
Yeah.
So this is for an interval, and I'm going to turn the graph off now. So let's see. There we go. So I'm going to turn the original rate graph off. Look at that. Approximate rate function. Pretty cool? Pretty good? And now we're going to go down to 0.005. So the one on the left you're seeing is for 0.0257. And now we're going to do 0.005. How's the rate function?
Extremely close.
That's still a step function. Those are still all little teeny widths of constant rates. All right? So, what happened? Are we exact yet?
No.
Technically not, but exactly, close enough, right? So it's like when we get to the point where we can't make a distinction between approximations, we call it a day. We say this is exact now. This is exact. Okay. Read Canvas carefully for assignment details.